So we're very happy to have Misha Belkin from UC San Diego. And I guess that he doesn't need so much of an introduction because we've been hearing about his work in the past 2 days a lot.
Well, thank you very much, Soledad, and thank you very much to the organizers for inviting me. It's great to be here. I really enjoyed the talks, and I would like to discuss something which I think is very much sort of in this line of trying to understand deep learning point of view. And what I'm going to present is joint work with my student Xiaoye Liu and Li Binju, who both really, I think, did exceptional work on this, really pushed this and explained a lot of things to me. Well, what's the sort of premise of this? We would like to try to understand something about why complex structures like this do certain things, right? They show good performance, they show certain mathematical properties, and they're kind of difficult to analyze. So we need to isolate some properties of the structure that we can understand and hopefully build on. In this particular talk, I will specifically talk about optimization. And so as we know, the models are obtained by some sort of algorithmic empirical risk minimization. We construct a loss function and we try to minimize it, usually by using SGD or some version of SGD. And I would really like to point out that I really like that quote from Ruslan's tutorial. He said the best way to solve the problem is you make sure you hit the zero trading error. Well, this is not the end of the trading, but this is the beginning, and then you can tune it and make it better. But you already have some sort of non-trivial generalization performance even at this point. So from the point of view of optimization, I think this is a very good point to start. Like, why is that we can get to the zero trading error? That's really the premise of my talk. I would like to point out that this idea that you will a very big system, I think it's useful to get some sort of perspective on that, to look at what people have actually been doing. And this is a nice summary of a number of recent architectures from Constancy et al. Each colored circle here represents an architecture, and the size of the circle, it represents a number of parameters that those networks have. So the small ones are about 5 to 10 million parameters. The big ones are probably on the order of, I think, 150 million. And the one I had first was actually not that big. It's only 6 million parameters. By modern standard, it's not very much. Of course, this is from 2017. Now we're, it's 2020. And the new champion is GPT-3, which has 175 billion parameters. And this picture is to scale. So this idea that more parameters in building a bigger system, as big as technologically possible, is clearly something that really is happening in practice. So let's try to understand from a more mathematical point of view why this is happening and what kind of properties there are of these systems that we can understand. And in particular, this talk, I will talk about two things. First, I will talk about why highly over-parameterized systems are easy to optimize, and I'll point out that they're actually non-convex in some very strong sense. And specifically, I'll show that they satisfy PL star conjugation. I'll explain what this is. And the second is this remarkable phenomenon of the constant NTK, which I prefer to call transition to linearity for the reason that I will explain later. And it's certain neural networks turn out to be linear when they're big enough. They implement linear functions, which I think is absolutely remarkable. So we'll discuss why this happens, and maybe I'll convince you that this is truly a remarkable fact. And this is based on these two papers specifically. Okay, so let me just get some pen. Okay, So next, let's take a view of this. So once you believe that the idea is to get to zero loss, you can take the interpolation perspective, which clarifies a lot of things. So what's interpolating perspective? Well, we're just trying to solve a system of equations, right? Getting to zero loss, if it's something like the square loss, it's the same as just to solve a system of nonlinear equation. You need to find W such that Fw of xi is equal to yi, where yi is labeled. But let's just think about binary labels to make it simple regression. Now, if I aggregate all of this f into a system of equation, I have f of w equals y, when y is a vector of labels, and f is a map from the space of parameters to the outputs on those data points. I'm suppressing xi's in this notation. So you can see f is the map from Rm to Rn. M is the number of parameters, N is the number of data points. Now, a fundamental question is, when can a system of nonlinear equations be solved, right? And of course, how do we solve it? Now, in this generality, this question may seem crazy because, well, if you sort of know like something like algebraic geometry, then essentially all of algebraic geometry is dealing with questions like this. And of course, it's a very subtle and complex subject. So how can I ask this question like that in full generality? But it turns out that, of course, it's not completely full generality, but there is a very large class of systems when you can actually answer this question. It's a pretty remarkable thing. And the other thing is that the obvious observation is that solving a system of nonlinear equation is equivalent to minimizing the loss, the square loss. Okay, now, if we sort of look from a classical point of view on this, we usually take the perspective that non-convexity is bad because there are many local minima, and there are no general global optimization techniques for non-convexity, right? There is no way that you can, by any local method like gradient descent, you can tell this kind of red global minimum from the yellow local minima. They look exactly the same. And then, of course, the question is, well, why can neural network be trained to fit data at all if this is true, right? They may just converge to some arbitrarily bad local minimum. And this is a very reasonable question, except this question lives in the under-parameterized world. In over-parameterized world, things are different. And this is a picture, a cartoon that illustrates the difference between under-parameterized and over-parameterized. So in under-parameterized, M is less than M. And the picture you have is like what I had in the previous slides. You have this isolated local minima. In over-parameterized settings, you have more parameters than constraints, and you have manifolds of global minima. This kind of global minima, not local anymore. Although every local minimum is also global in the picture on the right. And you have these types of manifolds. Now, if you sort of look carefully at this, on the left, you can see that that picture is still locally convex. What do I mean by locally convex? That around each minimum, right, in this kind of neighborhood, the function is convex. Of course, when you go wider, it's not convex anymore. On the right, this is not the case. The function is actually nowhere convex. And let me explain why this is the case. It's a really simple argument. Just look at a small neighborhood of one of these global minima at the bottom of the valley. Take some circle, some ball around it. If my function is locally convex in that ball, then the minima of such a function have to form a convex set. That means that this curve must be a straight line. So as soon as you have any curvature of the set, you cannot have convexity. And of course, if you have arbitrary, networks, why should you have convexity ever, right? Because it's always going to be curved. So essentially, this shows that in the over-parameterized world, we never get convexity at all, even locally. But never, of course, this is a generic statement. You can set up something very special, and you can. there are some questions. I guess I don't know how to. Maybe I'll deal with questions later. Okay, so I think the kind of summary of this is that the theory of optimization for over-parameterized system cannot be based on convexity. I think that's an important conceptual step. Now, okay, if it cannot be based on convexity, okay, it's easy to say it cannot do this, cannot do that. What should it be based on? And there is actually a perfectly fine alternative to convexity, which is not even new. It's 60 years old, almost 60 years old. And it's in fact well known but somehow not really widely appreciated, I suppose, although recently it has been becoming more popular. This is something called Polyak-Lyasevic condition. And the condition is very simply is that the gradient squared of my function is lower bounded by some constant times the loss. So this is PL condition for the loss, minus the loss at W star, which is the minimum. Now, if you look at it, you see this is a beautiful condition. This is first order condition. It guarantees convergence of gradient descent, and it's invariant at a nice transformation, unlike convexity. And let me just very briefly, I think this is a really important point. Let me just very briefly mention this. Why is this invariant under transformations, but why is convexity not invariant? So here is what's happening. If you're changing, so this is a very simplified version, so you can think of phi being L. Or the other way around, F being L. So when you compose two functions and take the derivative, right, the derivative just multiply. If both of them are separated from zero, then the product is going to be separated from zero. So you just need to make sure that each one of them is not close to zero. And it's easy to see that PL condition is completely compatible with that. Now, what happens with the convexity? Well, remember, convexity is the second derivative needs to be positive. Now, if I take second derivative of the composition, and suppose this is positive, then I have two terms. The first term is positive because it's the second derivative times something squared. But the second term contains first derivatives. And this you have absolutely no control. Just think about functions in one dimension, one variable. You actually have no control over this. So convexity is not invariant even under Nass transformations. You can break it very easily. And that's why actually on manifolds, it's a tricky thing. You could consider geodesic convexity, but that really requires you to be very careful. You have to take this geodesic basis of coordinates and then write everything in this basis. So it's a tricky thing. PL condition, you don't have this problem. Okay, so now going back to PL. What's the issue with PL? The problem with PL condition is that it has this annoying L of W star here. And L of W star is not known, right? Because to know this, you have to actually know the minimum. And that seems to be the chicken and egg type of problem. You have to know the minimum to verify, but before you verify, you cannot make sure that minimum exists. Annoying. Turns out that it's really easy to fix too. And how do you fix it? Well, you just get rid of the annoying term, cancel it. So now what we call this PL star condition, it's sort of a trivial special case of the PL condition. You just remove that term. And amazingly now, you have all properties before, well, which is not surprising because it's a special case of that condition. It is pointwise verifiable. And in addition, it guarantees existence of solution. So if you can just verify this at every point in a ball, you cannot just do it at one point, you have to have it held in a ball, then you guarantee that the solution exists and you don't need to worry about L of W star at all. Of course, it will be zero in that case. Moreover, unlike the other solution, this actually also guarantees convergence of SGD with fixed step size. Okay, so now this PL star condition, well, what good is this? We need to somehow get back to deep networks and over-parameterized systems and so on. And here are the kind of logic of this. First, the first point is that PL star condition for L of W in a ball guarantees the existence of a solution. And that's essentially the same argument as Polyak used originally for convergence of gradients. Second, PL star condition for the loss function is controlled by the smallest eigenvalue of the tangent kernel, and I'll get to that very soon. And third is that over-parameterized neural network satisfies PL star condition. Why? Because you can somehow control this eigenvalue. So that's basically the logic for the optimization part of the talk. Okay, now I'm going to go through this point and sort of at least give some idea why the things are true. It's actually not particularly difficult to see that all of this must be true. At first, what is tangent kernel? And I think probably everybody knows already, but let me present it in this form. Suppose you have a map Rm to Rn. If you have a map, then you simply have a derivative of this map, and this derivative is a matrix. It's a m by n matrix. Then the tangent kernel is simply df times df transpose, and this is an n by n matrix. So a tangent kernel is n by n valued function, really, because you can compute the derivative, this derivative times derivative transpose at every point. Okay, good. So now we have this tangent kernel. What good is this tangent kernel for? And the first observation is that tangent kernel, so remember my PL star condition had that mu in it. That mu is the smallest eigenvalue of the tangent kernel. And the proof is really almost trivial. It's, you know, 2 lines of basic elementary linear algebra. You just verify that this is true. For the square loss, I should say. This is for the square loss. If the loss is not square loss, it's still true, but then you have to worry about the loss function. Yeah, so now we know that instead of checking PL condition directly, which is kind of not clear how to do, we can just look at eigenvalues of the tangent kernel. Why not just look at eigenvalues of the tangent kernel and not worry about PL star condition? You can, but PL star condition somehow seems to be a more fundamental object. It's like convexity, right? Convexity, you can prove that the function is positive, the second derivative, the Hessian is positive definite. That's equivalent, that's sufficient for convexity. But it's more convenient to talk about functions being convex rather than dealing directly with this positive second derivative. Okay, now, so now that we see this, we can say that a system of nonlinear equation, that is essentially Pollack theorem with some sort of mind reshuffling, well conditioned in a ball of appropriate radius, lambda min, is, but by well conditioned, I mean that lambda min is separated from 0, has a solution in that ball. So now we reduce the existence of solutions to just checking that lambda min is bounded away from 0 in that ball. The radius of the ball depends on lambda min. So I'll have something for SGD when I have this explicit, but I don't know the right formula. So the ball needs to be sufficient. Basically, the smaller the lambda min is, the larger the ball needs to be for this to be. This is even true if you think for linear equations, right? Because when the system is poorly conditioned, the norm of the solution is going to be large in general. Okay, now a kind of consequence of this, sort of some extra thing on top of this, is that gradient descent converges exponentially to a solution at the red controlled by the condition number, which is lambda max divided by lambda min. But lambda max and lambda min here are different objects, so it's a slightly non-standard condition number. On the other hand, for the square loss, we don't really have to worry about lambda max because if there is a simple upper bound, basically based on the Lipschitz condition. So it's lambda min that's really the key here. And I should say that if my system is actually linear, this is a standard condition number. So it's a true generalization of the condition. Okay, so now that's maybe kind of the summary of this. Is that well-conditioned nonlinear systems, by well-conditioned I mean that lambda min is away from 0, behave like linear system under gradient descent, except that their condition numbers are non-constant. So that's kind of nice, because even though like the systems can be highly nonlinear, we can just think of that we're solving a system of linear equation for gradient by you know, Richardson iteration or whatever you call this. For there are Landweber, there's various kind of variations of gradient descent for linear systems. Interestingly enough, under-parameterized, this is only true for over-parameterized system. Under-parameterized system cannot be well-conditioned. It's not possible. But over-parameterized system almost always are. I'll explain in what sense. Furthermore, you can actually extend it to stochastic gradient descent, and you can show that stochastic gradient descent if you have conditioning in a good big enough ball, and here the ball needs to be bigger than for gradient descent. It doesn't quite match. But the same, essentially the same thing is true. You get exponential convergence for stochastic gradient descent, in fact, with fixed step size. Again, this is not true in under-parameterized. Okay, so now why are over-parameterized tangent kernel well-conditioned? And let me try to convince you that this is really a general thing. Whenever you have enough parameters, you're going to be well-conditioned. Why? Because of the following simple argument. So let us think about what happens when you have an over-parameterized system. That means that your M here is bigger than N, right? And my derivative matrix is N by M. So I'm multiplying N by M matrix times M by N matrix to get N by N. Now let us think, what does it mean for this matrix to be well-conditioned? That means that the row rank of my matrix GF of this matrix needs to be maximum. But this is really easy when it's skinny. Because, well, why? Because think about, suppose N is equal to 1. That means you just only have one equation. That's a single vector. What is condition number of a single vector? It's a minimum, it's a maximum value of that vector. So the only way in which a single vector can be degenerate if all the entries are 0, but it's a long vector, it's very difficult for all entries to be 0. Now think about two vectors, it's essentially the same thing. If I have two vectors and suppose they're like Gaussian random, then they're actually going to be close to orthogonal if they're long enough. So you'll have very good condition number. They're basically going to be maximum condition number. So as long as M is much larger than N, this is almost a trivial thing. And for Gaussian random matrices, in fact, you can do it analytically. The result explicitly analyze the condition number. And then it converges to 1, basically, in that limit when M goes to infinity for fixed M. That's kind of the example of two very long random vectors. So that's the intuition. Basically, skinny matrices are generally well-conditioned. And second, this only works for over-parameterized kernels, because under-parameterized kernel, you make this product goes the other way around. M is bigger than N, so the row rank will be deficient. So you will have always 0 eigenvalue of the kernel matrix. So this kind of phenomenon doesn't exist in the under-parameterized world. Okay, very good. So this there are now, well, how do you control condition number? So this is an intuition why matrices should, why tangent kernels should be well conditioned. That of course is not enough, right? You cannot just say, oh, okay, they should be. Well, great, but how do you actually show that? You can think that there are two ways to control condition number. One way is that notice that my kernel is essentially the first derivative. And how do I know how much the first derivative changes? Well, I need to control the second derivative, because the second derivative is a change of the first derivative. So if I can prove that my kernel is well conditioned at 0 at the point at initialization, and that my Hessian is small enough in a sufficiently large ball, then I'm good. Then I can control a conditioning number in the whole ball. So that's what we call Hessian control. There is another way to control, which is a composition control, is that if you have a system which is well conditioned and you do a transformation, which somehow has non-degenerate Jacobian, then the resulting thing is also well conditioned. That's a very different way to control the thing, using this compositionality of EL conditions. And this actually gives me a nice kind of segue into constancy of NTK, because to use this Hessian control, it's actually nice to know something about the kernel, about the Hessian, and that relates closely to the constancy of NTK. Maybe if there is like a question or two I can answer. I thought there was some in chat, so I can, before I start with.
The questions are not for you, so you can continue.
Okay, makes my life easier. Okay, so then let me talk about the constancy of NTK, which I think is like totally remarkable thing discovered by Jacob, Gabriel, and Hogler in 2018. And what they found is that the tangent kernel is constant for some infinitely large system, or close to constant. You don't say what constant means. And let me sort of give you a different perspective on that, and then I kind of go back to this Hessian control. Once we have this helps us with Hessian control. But this is a separate phenomenon, and it's totally remarkable in my view. So what is happening here? And first, let me observe the following: that a function is linear in a ball if and only if the tangent kernel is constant. Notice that this is not an obvious thing. You may say, oh, well, it's a derivative. It's not quite the derivative. So let's think about a function of one variable. Then tangent kernel is the norm of the gradient. The fact that the norm of the gradient is is constant, doesn't automatically imply that the gradient is constant. You can imagine that it can kind of rotate, keeping the same norm. It's not too hard to prove that it must be the case, but it's not an obvious. If you just like say, okay, it may be. But in any case, it can be shown. There is actually a paper which does it more generally for some manifold case. Yeah, so that's why constant NTK is really transition to linearity. Why do I prefer to talk about as a transition to linearity rather than constant NTK? Well, constant NTK is like saying the derivative is constant, right? Function is somehow, imagine that I have a function which is constant. Should I think of that function being constant, or should I say it's a function with derivative 0? It seems that the more fundamental description is saying that the function is constant rather than to say something about the derivative. So really, I think the underlying phenomenon is that these large networks become linear. And this kind of consequence of this is constant NTK, which is really equivalent. Okay, now, how do you think about this transition to linearity? And let me point out that you can, in principle, transition to linearity in several ways. So somehow these big systems become more and more linear. Well, let's think how can this happen? Well, let's write down the Taylor expansion for f of w. And this is in some ball, you can imagine. Now, well, how do you transition to linearity for something like this? Well, there are a couple of ways. One way, if you have a function like that, you can simply rescale the function. You can, instead of f of w, you can multiply by some small number, 0, 0, 1. Now it's actually closer to linear. Well, it's close to 0. So that's one way. The other way, you can rescale the input. And you can, instead of f of w, go to, multiply the argument by some small number that kind of, imagine it's like on a rubber kind of plane, right? You kind of extend this rubber and make everything flatter. These are kind of not interesting transitions to linearity. The interesting one is when you keep f of 0 and df of 0 fixed and only rescale the Hessian. So as your network becomes wider, right, maybe f of 0 doesn't change, df of 0 doesn't change, but the Hessian becomes smaller. And this is really what happens. And I think it's far from obvious, sort of at least from general principles, why something like that should happen, but I'll be more specific. So here is a kind of key theorem here. And the key theorem is simply that if you take a Hessian for a neural network, and here I would like to point out a couple of very important points. First, every layer has to be wide. Second, the last layer has to be linear. I don't care about all the rest of the layers, but the last layer, the output has to be linear of the previous layer. Then the norm of the Hessian, the spectral norm of the Hessian, is of the order of 1 over square root of m. There are some log factors which are increasing. It's like 4 tilde. So In contrast, f of w itself is O of 1. So the output is O of 1, and the gradient stays O of 1. So it's only the Hessian that rescales with the size of the network. And this happens in a ball of any fixed radius around initialization. And one thing I would like to point out that very often this NTK is somehow interpreted with respect to optimization. This has nothing to do with optimization. This is just a property of this functions class, that they become linear. Now, a kind of corollary of this, and it's almost obvious from that way, is that wide networks have PL star in a ball around initialization. Well, okay, I should say, if they are well conditioned at zero at initialization, then they automatically PL star because my derivative, the second derivative goes to 0. So you get it for free. And then, of course, you have to actually check that they are well conditioned at the initialization point, which can be done. There are a number of works which check this. And this is actually related to like big line of work on convergence of over-parameterized neural networks. Okay, so once it's PL star, of course, we get convergence for free. So it's kind of a very general. I think in a sense it's maybe a generalization of this techniques because it's okay. I don't know. Is it a generalization? It's a different way to view it, maybe. Because basically, you get from the Hessian scaling, you get PL star, and then you get convergence. Okay, so now let me tell you something about lazy trading and why there are some. I would like to point out, because I think this is commonly interpreted incorrectly, this whole thing. And the kind of intuition that is often given for this is something like this. Is that when you train, each parameter changes just a little bit. And if parameter changes a little bit, you stay close to the initialization point. And if you're close to initialization, the linear part dominates the tail expansion, right? And it sounds very plausible when I write it like this. And I think there are many papers which actually provide this explanation. This is, unfortunately, doesn't quite work like this. And let me point out the issue with this explanation. So what does it mean that each parameter changes just a little bit? So all of the thing is true except for the linear part dominating the tail expansion. So small change of each parameters mean that the difference W star minus W0 in infinity norm is small. It's actually 1 over square root of n, but it's little O of 1. But notice that the infinity norm of that vector has nothing to do with the Taylor series. The Taylor series is controlled by the by the 2 norm of that vector. And the 2 norm, because every one of them is 1 over square root of 1, but the sum squared of them is O of 1. So the 2 norm is actually not small. So you cannot deduce from the fact that the infinity norm of the change is small. You cannot deduce the fact that the function becomes linear. You see, when I have this two, I have the 3 things here, right? 1, 2, and 3. 1 is correct, absolutely correct. 2 is unclear. What does it mean to stay close to initialization? In what norm? How do you measure this? So if you measure this in infinity norm, this is true. If you measure it in 2 norm, it is not true. You are one unit away from initialization. Now, to have this implication, you have to have 2 norm, not infinity norm. So at this point, there is a little bit of kind of switch between the different norms. And that's why this argument doesn't work. In fact, not only small change of individual weights doesn't explain NTK, but it is actually not sufficient. And I'll give an example of this. So you can prove that when the last layer is nonlinear, you still have small change of individual norm, but you don't have constant NTK. All right. Let me now give a specific example, which I hope will clarify this. So what is an example? Example is a very simple 2-layer neural network with the last layer being fixed. So I'm just fixing this to be this plus or minus 1. I shouldn't do sigma. How do I erase this? In any case, so these things are plus or minus 1, and wi's are Gaussian, and I'm only training wi's. Okay, so it's a very simple example. Now, if you check, because it's normalized by 1 over square root of m, it's a sum of m random variables with expected value 0. So the sum is of order of square root of m. When I divide by square root of m, I get the output is O of 1. Now, if you check the kernel, you also see it's O of 1, just because it's a sum gradient squared. It's easy to check. But when you look at the Hessian, you realize that this Hessian is not just anything. It has a pretty interesting structure. It's actually a diagonal matrix in this case. And it's a diagonal matrix with essentially constant entries on the diagonal. They're not constant, but they're O of 1. So this thing is O of 1, and I'm dividing it by square root of m, and they're all on the diagonal. So that means that the spectral norm is going to be 1 over square root of m. Notice, this is because of the structure of the Hessian. It's not because of the size of the entries, because if I kind of like bunch up all these entries and put them in one corner, my spectral norm will be 1, and it will not be small anymore. So it's because it's diagonal that this happens. So that's basically the kind of effect that is happening here. Now, so I said, okay, well, it is diagonal, but you can say, okay, more generally, it's not going to be diagonal if it's not just a two-layer neural network. It's a more complicated thing. Diagonal is very special. So is there some sort of more fundamental reason that this thing is 1 over square root of m? And yes, you can say that there is something related to norm, and it's actually quite interesting. So a more general view, you can say, well, what is Hessian, right? In this case, Hessian is d squared f divided by dw squared, right? And if you write it w as a function of I'm sorry, alpha is a function of w, so you call these things alpha. These are the activations. Then you get this formula that Hessian is simply this. Notice that I should really have one extra term here, right? Because when you take a second derivative, there are two terms, remember the sum. Well, everybody knows that's from high school probably, or should know in any case. But there is only one term here. Why? Because the last layer is linear. So one of the terms disappears. That's a magic. That's really important. Now, well, what does this mean? This means that you can actually have a bound like this, which is essentially a Hölder inequality. Why has this funny 2-to-1 norm? Because really it's a tensor. But yeah, so this is what you need to see. This is infinity norm, this is 1 norm. And now if you check, you realize that this infinity norm is of the order of 1 over square root of m. So f, derivative of f with respect to the activation function is 1 of the square root of m. And this thing is of the order of O of 1. That requires some checking. In this case, it's really easy to check. In general, of course, it's more complicated. So what does this mean? This means that the product, the spectral norm, is bounded by essentially the infinity norm of df over d alpha. Now, k of w, the kernel, is actually also relates to f of alpha. It's essentially of the order of df over d alpha 2 norm. But because each activation depends on the parameters just a little bit, the 2 norm and the infinity norm are off by a factor of square root of m. So what is happening is that the kernel is controlled by the 2 norm. The Hessian is controlled by the infinity norm. And infinity norm is 1 over square root of m of the 2 norm. And that's why the Hessian norm is smaller than the kernel, the derivative essentially. This is the gradient of the same. Oh, sorry, this is gradient, the same order, also of 1. Now this is for 2 layers. If you have more layers, you have something similar, and the formula gets significantly more complicated with more layers, but it's essentially the same thing. You have df over d alpha 1, which is the first hidden layer, and plus df over d alpha 2, which is the second hidden layer, and these are all infinity norm. If you have many of them, it's you just sum them up. Now there are other terms in this which you have to control, but they're all like kind of O of 1. And these are all of 1 over square. So that's basically the maybe a little bit deeper kind of reason that something like, that is true. It's really a mismatch between 2 and infinity norm, which happens. Now, of course, the question is, well, okay, so I gave this fairly complicated explanation for this based on some mismatch between some norms, but is it really the case that is this the right explanation? So, okay, I cannot really like claim this is the right explanation, but let me point out that it does account for something which is important and which we see empirically. I'll demonstrate empirically in a moment. And kind of the reasonable question is, well, is linearity a general property of large systems, right? I already implied that it's not, but why not? And so what's happening here is that, let me give you a very, very simple counterexample. And I'm going to take exactly same neural networks as before, except I'll just put one linearity on the output. Now this nonlinearity phi can be just anything. It really doesn't matter what it is. And I'm claiming that as long as the phi is nonlinear, Hessian control will fail. The Hessian will not be 1 over square root of m. And actually, this is the same formula as before. It's essentially the fact that now this second derivative will have an extra term, and this term will be of the wrong order. So what is going to happen, I'm not going to go through it's easy to see I can just plug in the formula, but it's going to become too much notation. So this thing is going to be of the 1 over square root of m order as before. But the first term, the term which doesn't vanish anymore, the second derivative, right? If phi is linear, this term is 0. When phi is nonlinear, this term is not 0. And it's easy to see that as long as it's not 0, it's going to be of the order of 1. So the second derivative does not go to 0. It always stays of the order of 1, and you don't have constant NTK. You don't get transition to linearity. Well, all those other arguments fail. However, and this is, I think, a cool thing. If you think about it, this is still well conditioned as long as this phi prime, the final layer nonlinearity, is actually non-zero at 0. So I guess I can just say that it's not 0 everywhere. So as long as it's the nonlinearity has non-zero derivative, I have Hessian control, and my PL condition still holds, even though the thing is nonlinear and the tangent kernel is not constant. So convergence follows from this general result, and you can still prove the same thing. So what this shows is that having constant NTK is really not necessary. It's not a general condition of linear systems, and it's really not necessary for convergence. It's really PL. It's really not constant NTK. And let me demonstrate this sort of numerically. Yeah, this is really a reality. This is not a shortcoming of analysis that somehow we didn't bound something correctly. Maybe this term still vanishes for some reason. No, actually, no, it doesn't happen. First, we can prove that network with nonlinear last year have non-constant NTK even as the width goes to infinity. And second, I think we can just do it numerically to verify this. And here is what we're seeing here. And if we look at the picture, the black one is a linear neural network. I'm sorry, it's not linear, it's the last layer is linear. The red and blue are nonlinear. So this is linear last layer. And on the x-axis, I have neural network width, so I'm increasing the neural network width. On the y-axis, it's a relative change between the tangent kernel at W naught and tangent kernel at convergence, which is like we had some stopping condition. The loss was smaller than something 10 to the minus 3 or something. I forget exactly. So of course, if my tangent kernel is exactly constant, this would be 0, right? On the y-axis, I will have 0. So you can see as my network width grows, the linear last layer becomes more and more constant. This is exponential scale. So for like 10 to the 4, 10,000, width 10,000, right? It's 10 to the minus 3 roughly. So it's almost constant. On the other hand, for nonlinear last layer, it essentially doesn't change. The change between initialization and the convergence, the tangent kernel changes always by O of 1, no matter. So this demonstrates that there is no NTK regime, even though the systems are very large and they're highly parameterized, but it doesn't matter. So that it's just the fact that that term doesn't disappear when you take the derivative, the second derivative. That's it. So kernels of wide networks with linear last layer do not change along the optimization path. Well, more generally, the systems are linear, so they cannot really change at all. Kernels of wide networks with nonlinear last layer will change independently of the width. Now you can say, well, okay, maybe this is just something to do with the last layer. Maybe the last layer is special because you can kind of think the rest of the thing is linear, right? Only the last layer gives something weird. So maybe I can somehow get rid of the last layer. No, it actually doesn't work quite like that. So now look at the bottleneck layer. So imagine I have my last layer is linear. And I'm inserting a bottleneck layer in the middle. Now the question is, well, this is a highly over-parameterized system, right? Because all the rest of the layers are very wide, except for this bottleneck. Would I still see transition to linearity? And what you see that in what we can actually prove, if even when this bottleneck layer itself is linear, transition to linearity doesn't happen. You need every layer to be wide. And this actually graph illustrates this. When the width of the bottleneck layer is small, you have a large change from initialization to convergence of the tangent kernel. But as the width of the bottleneck increases, right, when it's like 1,000, it essentially goes down to 0, exactly as you expect, because now every layer is wide at that point. And yeah, you can actually prove that this is mathematically true. For bottleneck neural network tangent kernel, Hessian, I should say. I know this is really for the Hessian. Hessian does not scale as 1 over square root of n, even when the thing is linear. So the point being is that this is a rather subtle aspect. It's not something general for big system. It's something quite subtle, specific to the way these neural networks are constructed with these layers on top of each other, each layer being wide and connected to many things. Okay, now, so I'm closing to the end. Properties of our parameterized systems. So I think here is a summary. Deep networks are non-convex, even locally, but they satisfy PL star condition, and they behave like linear systems in optimization. By like linear system, I mean that if you control the condition number, even though they change, it's okay. Now, neural network with linear last layer are actually locally linear systems. They don't behave like them. They are systems which are linear, at least in a ball-around initialization. And transition to linearity happens as a result of mismatch between this norm. So it's a rather subtle kind of internal effect relative to the structure of the Hessian for these networks. Not a general property of large system, not explicable by just locality. So you cannot just say if you're close to the origin, this is true. And remarkably, this is not necessary. I really would like to emphasize this. This is not necessary for optimization, because the fact that over-parameterized systems are well-conditioned is kind of a generic fact. Once you have a skinny matrix, it's going to be well-conditioned if it's random enough. And when you initialize them at random, somehow it is random enough. So really, you can imagine a world in which this transition to linearity would not happen at all, but everything would still converge nicely on the optimization and the stochastic gradient descent. You really don't need it. What it does give us extra is that it allows us a simple way to control the Hessian, because it's enough to check that it's well conditioned at the origin, and that the Hessian is small, and then I'm guaranteed that it will condition in a ball. So somehow this transition to linearity or constant NTK phenomenon gives us some extra mathematical tool, which is really somehow not conceptually necessary. It's really kind of a remarkable thing. Like you don't really need it for deep learning, so I don't know why. It's a very bizarre thing. To me, it sounds a little bit like, you know, if you take a bunch of random numbers, right? And you subtract the mean, and you divide them by 1 over square root of m, suddenly you get the Gaussian curve. Well, why do you get the Gaussian curve? Well, who knows? It's not that easy to explain why you get a Gaussian curve. Well, we know mathematics, we can figure it out, but it's somehow magic. This is a little bit like that. Like you do something, you have some big system with some property. You look at it, turns out to be linear. Why is it linear? In any case, I think we still don't completely understand this thing, but it's, I think, quite exciting. Okay, so maybe I'll this is my last summary slide, and I think it's kind of useful to think about it in this term of this kind of double descent curve, which somehow separates modern regime from the classical regime. And in the modern regime, just talking about optimization, the difference from the classical regime, well, in the classical regime, you have this non-global minima, you have local convexity, but no global convexity, SGD oscillates, which I didn't really talk about. And somehow everything is kind of very tweaky here, right? Because depending on how exactly you initialize and do this, do that, things really change. In the modern regime, you have this non-locally convex landscape, but everything is PL, well, at least if you initialize at random, it's PL. I really should say it's PL star with high probability, because you can certainly find saddle points, but if you just do it at random, you're not close to any of them. It satisfies PL star conditions, so you get exponential convergence of stochastic gradient descent. And finally, which is kind of a little bit of a mystery, you get good generalization seemingly for free, which we still don't, I mean, we're starting to understand it in the linear, maybe in kernel cases, but it's still not so clear why this, you know, monster networks, when you get something good. So really, I think there is a way to, like, maybe the kind of final message is that we have to jump, you know, like Alice in Wonderland, right? She jumped into this rabbit hole, right? There was a strange wall there. So it's kind of like that with over-parameterization. And I'll stop here.
Thank you so much for your talk. There are a couple of questions. Maybe Yaim wants to open her microphone and ask her questions that she wrote in the chat. I'm sure that Renee has some questions as well. So. So maybe I can start with my question. So in your analysis, you have this conditioning this condition on the conditioning of your kernel that tells you that you satisfy this PL star condition, and then does this condition can be analyzed for models that are not the NTK? Maybe that's what you were trying to explain.
They are like this one. It's,
yeah.
I mean, I'm still, okay. This model is not NTK. Oops, where did it go? This is not NTK. The thing is, I'm still bootstrapping the analysis of NTK because somehow a part of this model is still NTK, and I'm using the fact that that there's some sort of transformation of them. So you can say I'm still kind of cheating and using NTK somehow through the back doors.
So
but it's not NTK as a model.
So that you don't need that in your training you stay within some small neighborhood of your initialization in order to have the.
That's guaranteed by the conditioning. So you don't but it's not that small. So that it's so I think I think that's a really important point. So what does small mean? And that always confused me actually. Mm-hmm. But I think I can be sort of give an answer now. There are two measures, at least, well, there are many more, but there are at least two measures to measure small. One in L infinity ball, in which it is true, it is small. And one in L2, which is not small, it's O of 1. It's constant.
Yes.
And that the second one is what matters for optimization. L infinity is really not that relevant, as far as optimization is concerned.
And in the over-parameterized regime, everything is very close in the infinity norm and not close in the 2 norm.
Exactly.
Right? Yeah.
Exactly. That's a disconnect. Because basically, when the vectors, right, have small entries, right, L infinity and L2 norms are quite different.
Another question that is related is that is a width assumption necessary for the PL star condition?
I actually don't think so, because what we see is that for bottleneck networks, they converge also fine. I don't think they're necessary. It's much harder to prove, though, without it. So I don't think we have a very sort of, actually, I don't know. It's a good question whether we can prove like for some specific examples, but it's certainly much harder in general. Because still the NTK gives us this wonderful method of proving things, even though it's not necessary. Any other questions?
There are some other questions in the QA, Soledad.
Oh, sorry. Another question is, could you elaborate on NTK for recurrent neural networks? And in this case, is it too general? Sorry. So if you can take temporal correlations into account.
That's a really good question. I don't know. We haven't looked at that. Like, what's a condition for it to have this 1 over square root of m thing for the Hessian for recurrent neural network? I don't know. Yeah, that's an excellent question, actually. It'd be very interesting. It's an excellent question. I don't have an equal. I don't have any answer. It's something very interesting, I think.
So another question is, could you comment a little bit more on what the bottleneck layers have to do with the style of the analysis you presented in the previous slides?
Oh, so what happens with the bottleneck layers when you have something like this? What you can prove is that basically there are some extra terms which appear because of the bottleneck. I cannot really explain it like that. But basically there are extra terms which are not small. So the Hessian doesn't vanish. It doesn't become small. It doesn't scale as 1 over square root of m. So essentially the condition we need is that every layer is bigger than m. The shape of the exact layer is not super important. You can have convolutional ResNet and so on, but they have to be wide. And when they're not wide, you can prove it. At least in some cases, you can prove that it breaks. You can give a lower bound on the Hessian.
But could you derive a result that is instead of the form 1 over the square root of the bottleneck size?
Yeah, that you can, yeah, because you essentially what you need is just every one of them needs to be bigger than something, right? So if your bottleneck is a very wide bottleneck, but the rest of them are even wider, that's fine. So you can kind of see what happens actually in this picture, right? You see what, even when it's like 100, which is still much narrower than other layers, but your change of the kernel becomes small.
So there's so many questions coming in the Q&A and the chat. So another question is, do you know if this PL condition holds for tensor factorization?
Like ICA time problems? I don't know, actually. I doubt it because it seems a very different. I don't think so. I think so there are this ICA type problem, independent components analysis type problems, when basically it's kind of like eigenvector problems, but they're non-linear, non-quadratic. You can show there that every minimum, so there are actually local minima, they're usually maxima. And every maximum is somehow interesting, and they all contain information, but they're not all zero. I don't think that the landscape, I think, is very different there. I think it's a very different problem. I don't think this analysis applies to that at all.
Well, but if you have a parafag decomposition, then like for just matrix multiplication, right? You can write that as a neural network with a single hidden layer, a linear network essentially, and the number of hidden layers will become the number of factors. So once you extend that to tensor in the parafag form, the number of sums that you have could be the width of your layer. And then you get a multilinear map that probably has the properties that you need.
Maybe, yeah, that's right. So some of them
you will
kind
just
of
need to do over-parameterized tensor
right.
factorization with the sum being sufficiently large, the number of terms.
That's right. Yeah. So maybe for over-parameter, I'm thinking more of like kind of classical ICA when it's not really over-parameterized. But yeah, actually it would be interesting to see where this transition is from under the over-parameterized. Yeah, I agree.
Okay.
I think.
I'm going to read one or two more questions, and maybe if Rene wants to ask his questions. So you mentioned over-parameterized models are well conditioned. Does that have implications on the robustness against adversarial attacks?
Yeah, that's a really interesting question. So they're well conditioned. That means somehow that the process of optimization is robust, that you get pretty consistent results no matter what you do, right? Mm-hmm. But that's for optimization, right? That's not for prediction. So I kind of feel that for prediction, as long as you're fitting your data close to exactly, and there is noise in the data, you are going to fit outliers, and you're not going to be robust. Even if kind of on average you could still do fine, but you're not going to be robust. So you have to do something else. So this is a different type of robustness. This is robustness with respect to optimization.
So you describe a nowhere convex property which characterizes the over-parameterized loss surface. Do you have any examples of other loss surfaces which also have this property?
Other loss.
Surfaces.
I'm sorry, can you repeat the question somehow?
So it's in the Q&A. It says,
if I can, I should be able to see. Sorry, I don't see it. Is that you describe a nowhere convex property which characterizes that? Is it a bit, do you have any, oh, I see that one. Mm-hmm. Sorry. Do you have any example of other loss surfaces? So it's very, very easy to have this property nowhere convex. Mm-hmm. It's very easy, actually. And here is what you do. Here is the intuition why this is so weird. Take a cylinder, okay, like half pipe. So it looks like this. This is convex, of course, but it's not strictly convex, right? Because there is this direction, which is 0. And now just twist it a little bit. It's nowhere convex. So when you have something which is not convex, not strictly convex, but just convex, it has zeros, and you just twist it a little bit, you always break convexity. Because convexity means curve which is 0 of the 0 set. And any small twist will break that. So it's very, very easy. Once you over-parameterize, once you have manifolds of zeros, it's very, very easy to be non-convex. In fact, it's very hard to be convex because you have to literally be just like straight. So everything has to be on the affine value. So that's a kind of nature of this. And that directly relates to the fact that it's not invariant, that convexity is not invariant under transformations. There is another question. A quick move from chat. Are there references you would suggest which give you very theoretical justification for the double descent curve? Oh, there have been quite a lot now. Some of them were discussed here. Yeah, I mean I sort of hesitate to name anything specific since there are like number. But yeah, I think other talks have discussed exactly this question. So that would be a good thing.
Okay, so thank you again, Misha, for your talk. And I think that now we have, yes, we have the final
Thank you
remarks.
very much.
Thank you so much.